Like she said, my name is Robert Hernandez. I'm a veteran of the United States Marine Corps, and I've been working with the Department of Chemistry and Chemical Biology under the Whitesides group. My presentation is on the rapid fabrication of complex nanomaterials using Shadow Sphere Lithography. Shadow Sphere Lithography is a technique that we've been using at the Whitesides group, and we aim to make complex nanomaterials, nanoantennas that can manipulate the propagation of visible light and infrared light on the nanoscale. Currently, something that we use some of these templates for is that manipulation of visible light like a flat lens, shown right here. We're tackling this problem by using Shadow Sphere Lithography, and the idea is to use the shadows cast by beads, as you can see right here, and using multiple angles of deposition to create complex materials using the space in between the beads. Right here we have a 1 millimeter wide template in a quasicrystalline pattern. This is the next generation of Shadow Sphere Lithography that I've been working on over the summer. And the idea here is to, rather than using a random assortment of beads that are self-assembled, to actually control where the beads are on the wafer. This is 100x magnification, so you can see the pattern is fairly complex, but is uniform throughout. And right here we have the size of the hole itself is 4.8 microns, which is about 95% the size of the bead for mounting. And what we're going to be focusing on is actually the space in between the beads, which is about 150 nanometers wide. This process is done by first mounting the beads on a silicon wafer and applying PDMS to remove it from the template. Then we coat a fresh wafer with PI, or polyethylene, and then use that same PDMS to transfer it to a fresh wafer and use a plasma etch process to remove the excess material. What we end up getting is this image right here you see up top is about a 90% transfer rate from the original template to a fresh wafer, which is really great compared to what we had earlier this summer. What happens is that after we do electron beam deposition, we end up with these complex structures you see right here. This structure was created using the quasicrystalline pattern, depositing gold at every 72 degrees around the beads. Right here we have a zoomed in view, and you can see the hole in the middle is actually where a bead sat. It's about 5 microns wide, and you can see each individual deposition at every 72 degrees. And what we're focusing on is, again, the spaces in between the different deposition levels. After fabrication, we actually decided to put germanium down on silicon wafers, and you can see right here that we have a couple of defects. This is actually towards the edge of a template, and the defects right here actually took the germanium at the same rate that the beads did, helping to show that this process was scalable. And we're working on in the future to use a smaller scale deposition on the 1.5 micron scale. You can see right here on the bottom left-hand corner that the brighter spots are actually thicker layers of germanium. And again, it's kind of hard to see, but if you can focus on the different layers in between the bead positioning, that's actually the complex structures that you can see there. And as a reference, on the upper left-hand corner, that's the 5 micron wide bead. And then we have a zoomed in view of the germanium. Again, we have the different layers of deposition, different thicknesses, and the complex structures in between the bead positions. Before I go to my next slide, I want to show, I actually have right here a quartz template that we use for manufacturing the templates. Now, I also have a sample. This is a perfect recreation of the design that we create on the software. You can see it right here. It's kind of small, so bear with me. And then we have a template that we created in the lab. This is a sample. This is actually an allocation of beads on a glass template. So we have fairly high quality transfers. Again, in the future and towards the end of the summer, we've actually been working on scaling this process down, and we have preliminary results on getting this process down to the 1.5 micron level. Hopefully, with these nanostructures, we'll be able to interact with infrared and visible light, and again, act as a flat lens and be able to affect data transmission over large distances. I'd like to thank both my mentors, Dr. Nemirovsky and Dr. Ganadek, the Whitesides group, and of course CNS for allowing me to do all my work inside the clean room. And I wanted to thank Dr. Catherine Holler for allowing me to conduct research at Harvard University this summer. Thank you. Any questions? Yes.
I may have missed it, but you said you were shooting them at every 72 degrees?
Yes, our original quasicrystal design, we deposited gold every 72 degrees, which for 5 depositions adds up to 360 degrees. And the original images that you were seeing is more of a proof of concept rather than constructing actual complex structures with optical properties. But the idea was just to create a complex structure to prove that we could do it more than anything.
Right. My question is, I understand every 72 degrees around it.
Yes.
But if I treat that as my theta, what's my phi? What's the angle that you're approaching beads from?
Oh, we used you're talking about the angle of inclination. That was actually, we did 65 degrees off of 0, and then we rotated it. We did a deposition of gold every 72 degrees after that.
Did you try different angles, or is it just?
Oh, yeah, we did with the germanium. We used 45 degrees, and then we did depositions every, I want to say every 60 degrees for more deposition angles, but I don't have that data with me right now. Any other questions? Yes.
What are some of the potential applications of these devices?
As shown on the first slide, the idea is to create flat lenses. A lot of these microstructures are smaller than the wavelengths of light, and they can act as antennas for visible and infrared light wavelengths. So the idea is to manipulate the propagation of visible light, and maybe in the future encode light wavelengths with intelligence, similar to how we do with RF frequencies. Thank you very much.